Welcome to my presentation. I'm going to present our paper, Capacitive Near-Field Communication for Ubiquitous Interaction and Perception. I'm from Fraunhofer IGD, and I conducted this work together with my colleagues from Technical University of Darmstadt and University of Regensburg. So nowadays we're surrounded by objects. There are about 10,000 objects which a person possesses, or an average person in Europe. And nowadays these objects, or some of these objects, tend to become smarter. So we can see a lot of developments in that. And this poses a lot of challenges to application developers and also researchers. So for example, we have the challenge of power consumption and supply, where we have usually a very restrained battery, and we need to make a trade-off between communication abilities and the interaction possibilities and the power consumption and recharging. We also have a lot of constraints on embedding hardware, especially due to power consumption, placing batteries, and sophisticated sensors, as it is shown here in this smartwatch. And the unfortunate challenge of cost, which we don't like to hear as a researcher. Again, all these smart objects rely on some kind of communication. Nowadays it's mostly centered on smartphones, like you can control your oven with a smartphone, but it's also moving to dedicated devices such as this remote control for controlling a light. So this again refers to the topic of interaction, which is very important for smart objects because due to cost limitations, we're usually not able to provide very sophisticated user interfaces in smart objects. And interaction and communication is the main topic of our talk. And I would like to ask the research question how we can enable communication and interaction with everyday objects. And that means a lot of objects and also very low power objects. And this is an example of our first case study we conducted. Now I'm not going to dig into technology, but here we can see how we can interact with everyday objects and light, for example. And we can use these objects in very similar ways, like we would use them in real life. For example, using some bottles to fill up the light with different colors. And then, now comes my favorite part, use the whisk to mix all these colors together. And of course, this only works when you shake the whisk. We would also like to interact with these objects using our smartphones, for example, having some kind of a nicer user interface. But also, for example, through simple touches, connecting objects with each other, or using things like gesture recognition, where we combine an eraser, as it is shown here, with the smart lamp and then simply can move over the eraser to switch the lamp on and off. So our goal in our work is to combine short-range communication with rich interaction possibilities, as it is shown here on the picture. And here a lot of communication methods can come into place. For example, we got a lot of inductive communications, as in RFID, or commonly referred to as NFC. But we could also imagine using capacitive communications, which has the property of requiring a common ground between two communicating nodes. And this is actually a challenge we have to face when we design for such technologies. Currently there's a lot of communication taking place in the radio frequency regime, like Bluetooth or Zigbee. But in my talk, I would focus on the capacitive side, as it can support very interesting interaction possibilities. So there's been a lot of related work carried out in this field, which is composed of two different areas. One is capacitive sensing, where you could, for example, do gesture recognition using capacitive sensors in free space. You could also do implicit interaction, like fall recognition or capturing movements above a table. On the other hand, we have capacitive communication, where we've seen works in intra-body communications, for example, to transfer images from a camera to a computer and then print them, or very recently communication with ordinary touchscreens by smart artifacts like this finger ring, for example. So in our work we try to derive some common concepts out of this related work and present a framework that builds up on this and enables to realize capacitive communications with everyday objects. And as I said, one of the very important things we have to think of is that we require common ground coupling between two objects. And this ground coupling can be established by simply touching the object or moving into proximity, because the conductive properties of a human body enable this kind of ground coupling. We identified a set of 3 operating modes that can allow for capacitive communication, and the first one is ground coupling by touch. So here we see a little toy airplane communicating its acceleration data to the desk, for example, to play a computer game. And it is grounded by a user touching the object and then can establish communication in distances up to 15 centimeters. The second operating mode is based on a ground coupling by proximity. Here we have a receiver placed very near to the object, and by using a larger ground electrode we can detect the proximity to a human body part in distances up to 15 centimeters. And also, when we have a very strong ground coupling, we can do intra-body communications, which is usually based on very stationary objects, like this lamp, for example, having a common power supply. So these are the 3 operating modes we propose, and I will show later how to use them. But first, we'll dig a bit deeper into technology. So here we have an example of our technical setup. Again, we can see our toy airplane communicating acceleration data to the desk to play a computer game. And the transmitter is very simple, as we only require a microcontroller and of course an acceleration sensor, and then we put a simple square wave signal on one of its output pins to transmit information. The square wave signal oscillates at 10 kHz and is succeedingly turned on and off, representing ones and zeros. And this way we can achieve a data rate of 2 kilobits. On the receiver side, we require some additional hardware, namely a transimpedance amplifier that amplifies the incoming displacement current, and then a microcontroller that does all the signal processing and decodes the message again. And then, of course, hands it over to the PC. So here are some examples for electrode placements. Here we can see our lighter, which we've seen in the first case study. And it has ground electrodes attached to the body, and the transmit electrode is made up of the native material of that lighter. And it even works when the lighter is on. This is an example for a receive electrode, which is attached to a desk. And this way we can use all 3 operating modes. It's ground coupling by touch, proximity, and also intra-body coupling. And again, we need to have a ground electrode, and in this case it's the laptop's conductive body itself, which is very big, makes up a good capacitive coupling to ground. Here we can see a magnifying glass that can also be used to detect proximity to body parts. We have a very large ground electrode, and this enables us to detect human presence in distances up to 10 centimeters. The transmit electrode is attached around the glass. We also realized a smartwatch, as it is shown here, has a ground coupling with the inner ground electrode and uses a transmit electrode to transmit acceleration information. We evaluated all 3 operating modes, and the first one is ground coupling by touch. And obviously, when we use small transmit electrodes, small receive electrodes, we can communicate in distances up to 5 centimeters. But as soon as these electrodes grow larger, we can see that the distance increases, and we also found out that larger transmit electrodes are better than large receive electrodes. And this is a 3 by 3 centimeters electrode, and it supports communication in distances up to 15 centimeters. Regarding ground coupling by proximity, again, when using small ground electrodes, we can detect human presence in distances up to 6 centimeters. And when these electrodes grow larger, it is extendable up to 15 centimeters. And when they grow even larger, we can even communicate without body presence, just by the conductive coupling to a table, for example. In intra-body communication, we can see that the signal strength increases with the contact area when having or when placing one finger or a whole hand. This will change the behavior a lot. So here we can see the increasement, and this lets us detect changes in the contact area, for example, by adding or removing a finger. But due to offsets, we cannot tell if it's 3 or 4 fingers, for example. Now I'm going to present our remaining case studies. The one is on the analysis of sleeping behavior, which represents a use case in implicit interaction, and the tangible interaction for the visually impaired in explicit interaction. So here we have a receiving electrode as a conductive thread inside the bedsheet, and we have a smartwatch that transmits its acceleration data to the conductive thread. Again, here we can see that it's ground coupling by touch, and the receiver is stationary, so it's grounded very well. We also integrated a transmitter electrode at the foot part of the bed to detect presence of a person by sending messages through the human body. And now we can combine all these two operating modes, for example, to measure sleeping quality by measuring acceleration at certain parts of the body, but also by combining this with stationary sensors, as it is shown here, where the message is sent through the body and then identifies which electrodes the person lies on. We also conducted a case study on tangible interaction for the visually impaired. In this case, we have cooperated with the company producing these products, and of course this is still very experimental, and we need to refine that. So now here we can see a command card that can carry out screen reader commands, and by shaking it you get a description of what it's doing. And we can use the toy airplane to adjust the speed of the screen reader by leaning it backward or leaning it forward. And then we can carry out the command again and let the screen reader read it a bit slower. Okay, we also implemented an application launcher. This is kind of an ugly cloud, which represents the weather prediction service, mail client, and online banking. The magnifying glass can detect proximity and then give a description of what it's supposed to do. The magnifying glass can be used as a screen magnifier. And now you're able to move it and browse through the screen this way. So it's still very experimental, but we think that capacitive near-field communication can enable communication among a lot of objects. But we've also seen that blind people don't want to have thousands of objects on their tables, so here you will need to find a certain trade-off. And now I'm going to conclude my talk. With CAP NFC we can obtain a very good power consumption. It's currently very similar to RFID, which basically is constrained by our implementation. But when we look at the output powers, it is very promising, and we expect it to be much more energy efficient than RFID in the future. We can also very easily equip existing objects, as only a single microcontroller pin is required for transmitting information, and this also represents a very important cost factor. The embedding of hardware components is very easy. we only require just one additional hardware component for receiving messages and no additional for transmitting. We joined the two worlds of interaction and communication to a touch and proximity mediated communication, which I find is a very interesting research topic. Using CapNFC, we can bridge the gap between a high number of objects and very sophisticated interaction possibilities. Our work is also available open source. You can download it at opencapsense.org, so there you can find the schematics, board layouts, and also firmware files. Now I'm looking forward to your questions.